Okay, so as Nicola is coming, I will do this talk in English because we have a couple of non-French speakers in the room. Hello, my name is Clement escoffier. I'm working for Red Hat as a Vert.x core developer. And in this talk, we are going to see how we can develop in the next 45 to 50 minutes a couple of microservices that we will deploy on the cloud. Well, because I have some internet issues, the cloud is going to run on my laptop, but it's absolutely completely equivalent if you will run it on any Kubernetes platform like Google Cloud Platform or whatever. So I say that we are going to develop a couple of microservices, reactive microservices. But first, let's define what reactive means. And reactive means a software showing responses to stimuli. Whatever responses mean and whatever stimuli are. It's actually very, very vague as a definition, but it's a direct application of the definition of the word reactive from the Oxford Dictionary. In the reactive landscape, we have three different areas. The first one are reactive systems, which has been defined by the Reactive Manifesto a few years ago. And reactive systems can be simplified, well, can be defined as distributed system done right. The idea behind reactive systems is that everything is going to be asynchronous and all your system is going to interact using asynchronous message passing. And because you are asynchronous, you get resilience and elasticity almost for free. And so, because you have all these features, you get responsive. So you can survive, pick off loads, and you can still answer and handle the request, even if you are facing failures. The only issue with reactive systems is that they are actually very hard to write. Very, very hard to write. And recently, we have seen a new trend, a new paradigm in terms of development, which is reactive programming. Reactive programming has been launched a couple of years ago by Microsoft. Reactive programming and reactive extension. And the idea behind reactive programming is that you are going to compose your software, event-driven and asynchronous software, using one main construct, which is a data stream. And so you have a pipe where you have data, items, and you will be notified every time that you have a new item. And so as you are notified, you can react. And this data stream construct is natively and inherently asynchronous because you don't know when they will come. You just know, okay, if something arrives, I will be ready and I will be able to react. However, there is a big flaw when you are handling data streams. What happens if you get too much data and you can't keep up? First idea, we will put a buffer in between. Good idea. Except that your buffer might be full. And then what happens? Two things, out of memory, buffer overflow exception. In both cases, your Java program is dead, or almost dead. So we need a way to handle that. And that comes with the third part of the reactive landscape, which are reactive streams. Reactive streams is a very simple protocol to handle non-blocking and asynchronous back pressure. So what does that mean? That means that before pushing an event in my data stream, I will verify that the consumer can handle it. So the consumer will tell me its capacity, say, okay, I can handle 2 items now. And so the producer can say, okay, you can handle 2, I have 1, and as soon as I have another one, I will send it to you. So that's simple like that. Looks simple, reactive streams. If you look at the API, it's 4 classes, and every classes are very, very, well, simple. It's a couple of methods, and you say, oh, it's easy to implement. It's actually very, very hard to get it right. And passing the TCK took us, at least on the Vert.x side, a couple of weeks, if not months. So I mentioned reactive, but I also mentioned microservices. Microservices. Who said it's going to be simple? Before we had a monolith, and inside this monolith, everything was fine, everything was collocated. So calling another bean or something else, everything was fine because it was there. Everything is deployed at once, so no uncertainty. Microservices, we take the monolith and we say, oh, no, it's different process, different VM, different nodes, different part of the world, and everything is going to be asynchronous. Great idea. Except that you have you have uncertainty. No? You don't know if the service is out there. You don't know which version is there. You don't know if it will be able to handle your request. You have absolutely no idea what's going on. So when you move to this microservices world, you need a way to deploy, package, and keep your system on track. And for this, in this talk, I'm going to use Kubernetes and one distribution of Kubernetes, which is named Openshift. So first, somewhere, there is an operating system. Don't forget about it. There is something somewhere that is going to run and execute your program using 0 and 1. Then on top of that, we have Kubernetes. Kubernetes is an orchestration engine for your containers. You are going to deploy containers, generally Docker containers. I'm going to use Docker here. And it will keep everything on track, like the networking, the volumes, image, the registry for your image, metrics, security, and so on. On top of that, Openshift had one great feature, the UI. We'll see. The UI of Kubernetes is kind of weird. At least Openshift has a nice UI. It also had build and deployment automation. Build is cool because as soon as there is a change in your code, in your source repository or anything, or in your configuration, it will say, oh, there is a change. I'm going to rebuild your image. Your image is built here. Go in the registry. And if you have the right deployment automation policy, it says, oh, you have a new image. I'm going to update your running system. But it's not going to update it abruptly. It's going to implement a rolling update, meaning that you don't have downtime. We are going to see all of this. We also have in Openshift a service catalog containing, well, a lot of image, pre-built image for almost anything. I say that Kubernetes is about container orchestration. And there is one big misunderstanding about containers. Containers is absolutely not about isolating your process from another process. It's what you see. Containers is about sharing. It's about sharing the same CPU between 3, 4, 5 different containers. But remember, somewhere there is a CPU, something, a processor that is going to execute your process. So the question is not how easy it is to create a container. The question is your application ready to run in a container in a way it respects its siblings and peers? And actually, this is a big change, and right now, with the current technology, we are not that good with that. Why? Because most of the traditional technology here is using a lot of threads. Yeah, generally, we use 1 thread per request. And then we can handle, for example, in the HTTP request, we get the HTTP request, and we handle this over, well, we keep the same thread for the whole request. So if you have 1,000 requests, then you need 1,000 threads. Try to run a JVM in a container with 1,000 threads. Yeah, it works. But what about the other containers deployed on the same CPU? It doesn't really work great, because the CPU cannot handle everything. So what we do is just say, oh, no problem. I will put you a quota. You now have only a quarter of a CPU core. Neat. Okay, so first, you have a big thread pool with a quarter of CPU, so you are going to spend this CPU quota just switching between threads. It's not really great. You are spending time doing non-logical and non-physical code. You are just switching threads. Second thing, threads introduce a lot of memory overhead, a lot. A thread is not cheap, it's something big. So what we see here, if you have a big container here, is that, well, the memory is the same thing, it's shared. If you're writing the memory, the other one don't have memory. So what happens? Well, we put a quota again, but then your application needs to be developed to respect this quota. And you can start thinking, okay, so I need to tune my thread pool, I need to tune the memory I'm going to use, and so on. And then you realize that most of the runtime that we use in containers today are actually not made to be run inside containers. They are not container native. They might be cloud native, but not container native. So we need to fix that, and it's actually the main reason why we made Vert.x at the beginning, is we want something that is reactive, that can handle the load, that can build reactive systems, but in a way it's can run inside those things with respect of the other applications, so which will use the CPU and the memory in a very, very efficient way. So basically, when you run a traditional Java application, you have 100 or 400 threads. I'm going to use one thread per microservices. One. And I will be able to handle 10,000 requests per second without any issue. And we will see that. So enough talking. It's time to see some code, and let's start. So I will sit. It's better to live code. So something I didn't say, but we're also going to fix my first world problem, which is managing my shopping list. So for managing my shopping list, I need a shopping backend. So I'm going to create a shopping backend module. It's going to be a Maven module. Vert.x does not define whether or not you should use Maven or not, Gradle, Ant, Make, or whatever. You can use whatever you want, because there is one thing about Vert.x, is a freedom. We will see that. OK, so yeah, put it on Git. Git is fine. So I've just created this Maven module here, but yeah, that's very simple. So let's pimp it a little bit. I will go in shopping backend. I will copy a big command line that I will explain. OK, so I'm going to use Maven. I'm going to use a Vert.x Maven plugin. And it will take my POM file and just add a couple of dependencies, create a vertical. We are going to see what it is, and so on. So if I run that, my POM file will be a little bit improved. And here we go. So what do we have here? We have a vertical. We are going to see that. I defined the Vert.x version to 3.5.0, so the latest version we released a couple of weeks ago. We have a BOM file, but because we are hipster, we don't call that BOM, we call that dependencies. It's a BOM. Don't say it. Couple of dependencies. So Vert.x core is the only dependency you need to write a Vert.x program. And then we are going to use all of these in this session. And that's all. So now if I go back here, I should have created one class. It's a vertical. So vertical in Java is a simple class that extends abstract vertical. I said in Java because Vert.x is polyglot. You can use Kotlin, Scala, Ruby, Groovy, JavaScript, thank you. I'm forgetting a couple of other languages we support. Ceylon, and so on. And the first thing you will do is this. That's your hello world. I want to create an HTTP server, and for each request, again, reactive, for each request, I'm going to respond with a very interesting message, hello. And I'm going to start on the port 8080. So you probably want to be Java 8, yes. Yes, yes, OK. I'm done. This is a program. It will, normally, it should run. So let's try that. You don't have to use a Vert.x Maven plugin to run a program. You can just use barely any Java program. You can embed Vert.x, because, well, Vert.x, you can just create a Vert.x instance and just deploy the vertical on top of it. So it's really, you decide how you want to do it. But now, if I do that, oops, that's a cache, yeah. Here we have hello. So let's try one thing. Hello. Thread.getName. Let's see on which thread we are responding. And I'm refreshing here, and every time I'm using the event loop 0. Oh, event loop. What's an event loop? An event loop is a thread that has a message queue, gets the next message, look at a set of handlers, dispatch the message, and text, and do that forever. It never dies. It just gets the next, find the right handler, dispatch. Get the next. To work, we need to have the handlers in a way that they don't block the thread. If they block the thread, then you get the next event, wait, dispatch it. But if it's blocking, then the number of events will go in the queue, and the queue will grow, and then we're back to the first problem. How do you scale? So your code must never block. Obviously, this is realistic today. Most of the Java library are blocking. So Vert.x comes with a huge ecosystem, so most of the things you will do with Vert.x are non-blocking. And if you really want to use blocking code, we provide constructs that will let you run blocking code. Okay, but I said that I want to fix my first world problem, which is my shopping list. And my shopping list is going to be very, very simple. I will do a map, or model as a map, because the shopping list has to be modeled as a map. The key is going to be the product name, and the integer the quantity. And obviously, as it's a map, I will call that list, because things need to be a little bit confusing, right? Done. And now I want a kind of a CRUD or REST-ish API. Well, if I start doing things here, that's going to be hard, right? If I need to check the method, the path, and so on. So I'm not going to do that, and I'm going to introduce you a another Vert.x construct, which is named a router. So if you did a little bit of node development, this is exactly the same. Barely speaking, we copied them. So it's the same thing that we have in Express.js or in Happy. So how it works, it's very simple. It's a router. We will declare root on it. And for example, if I have an HTTP request on /, I'm going to just say, well, hello. And then it's RC. I'm going to define a couple of other routes, like on shopping, I'm going to do get list. Okay, she's not compiling this. Then if I post something on shopping list, we will do add to list. Okay, and if I'm doing something like a delete, because we can delete something from my shopping list, then I will use this strange notation here that say, okay, I have a path parameter, and and I will delete this product from my list. One thing I should not forget, two things. First, for performance reason, by default, Vert.x does not pass the body. So we need to tell him, hey, by the way, great. We need to pass the body, and so I can retrieve the body as a JSON object. And the second thing that I must not forget is to say, oh, okay, no, I need to use a router here. It's what I'm doing. So now, because we have this accept method in the router, every time we get an HTTP request, it will receive the HTTP request, look at the right route, dispatch on the route. Let's now develop these things. Oh yeah, don't worry about this. It's because it does not compile, and yeah, it's complaining. And as most of the Vert.x team is French, we know how to complain. Don't worry about that. We are very aware of it. So I want my list, and as I'm cool and I want to do JSON, I'm just going to do response and JSON.encode prettily, I'm an artist, to my list. Done. Add to list. So add to list is the same thing. I will retrieve my body as JSON. So as we do a lot of JSON in Vert.x, we have our own JSON object, JSON array abstraction. It's just because it's convenient to manipulate JSON. So let's say that we have the string name, and that is going to be my name, and I will also have my integer quantity, get integer quantity, and maybe it's not there, so I will say that the sensible default for quantity is 1. So I have my name and quantity. I will just do list.put name and quantity. And then, then I just want to display the list. Oh, let's just call get list. Done. I've chain calls. Remove from list is going to be almost similar, right? So I will get, I have this path parameter here. So name is going to be path parameters name here. So that's my name here. And then I will just do list.remove the name. And I will just call getList. So now I should have my shopping backend ready. Let's try. If I go back here, I have hello, so that's normal. And if I go to my shopping list, I have nothing. I need to add things. So I will just do HTTP post 8080 name equal slash shopping. So I'm using HTTPI. I don't know how to pronounce it. HTTPI, HTTPI. It's just a curl on steroid. I need coffee, and as you realize, I need a lot of coffee. 12. And now if I go back here, yeah, I have my coffee. And let's try to add something else, like, well, I also need tea. But not too much tea, because yesterday evening I did this mistake to drink one of your mint tea, and I had some issue to sleep after that. So now we have tea and coffee. And great, and I wrote tea as French. So I need to remove that. /shopping/tea, and now if I do that, then the tea is gone. Great. So I have my REST API, my CRUD API, done, but, well, I want to deploy that on the cloud. I want to deploy that on Openshift. So one thing to know about Openshift is that, or Kubernetes, it's not that simple from the developer point of view. There is many, many entities, and you need to understand a couple of them, and basically if you understand this picture here, you have understood everything from the developer point of view. You have source code. That's what you write. You are going to send this or a binary of this to Openshift. We will have a build configuration that will receive it and say, oh, I know what to do with that, and I'm going to write a Docker image. So it's going to take your code or take your binary and write a Docker image. And then we will also provide a deployment config. And the deployment config will say, oh, every time I have an update in the Docker image, I will deploy it. And we'll create something called a pod. A pod is a group of containers, traditionally one, but potentially more than one. So here we have our containers. But from my browser, here, I need to access the services provided by this container. So how does that work? I have my browser that will hit a root. A root is a public URL. It's a public URL that I can hit, and that will delegate to a service. And this service is going to delegate to my pod. So in red/orange, that's the OpenShift concepts. In blue, that's the Kubernetes concepts. If you use plain Kubernetes, you have things to do that, and you have some other tools to do that too. One thing interesting with this service ID is that if I have multiple instances of pod, it's going to implement a rolling update, round robin between the set of pods without doing anything. So if you want to do A/B deployment, you can also adjust the weight between both, and then it's going to work too. So you just have everything to build your system with that. Okay, but let's try this now. So as I said, I'm going to use Docker, and the first thing I will do is to write a Docker file. Docker for Vert.x is very simple. It's this. I need a Java image. Don't use that one. This one is deprecated since a couple of months, but yeah. I'm going to expose the port 8080. I'm just going to copy the file jar to somewhere in my containers, and just start it. So I have this here because by default Vert.x is, I think it's not true anymore, we changed it. Trying to write in the current directory, the cache, and it's generally not allowed in containers. Your current directory is read-only. So I just say on /temp because anyway, we are on a container, so when we die, we die. Everything is done, it's gone. So now I have this. So what I'm going to do is to, oops, that is weird. Oh yeah, I will stop this one, script, and build with, okay. Why don't I have the right one? Oh. Shopping backend, and no scripts, no. Script/build with Docker. Okay, so what it's going to do now is just create a default configuration for the build, default configuration for the deployment, do a Maven build that create fadjar. Well, fadjar, let's have a look to this fadjar. It's already there. So if I do shopping backend / target, it's 7 megabytes. That's a low fadjar. We have everything inside for 7 megabytes. So you don't have to think, do you need a hollow jar, do you need such kind of things? It's just 7 megabytes. It's nothing. Well, except if you have the current Wi-Fi. Then, yeah. And done. And so now, if we're here, we can see that we have this shopping backend here. We have a pod. We have a root. We have a deployment. So that's my configuration. We have a build. We can have a look at the build. If I go to the log, what happens is that we have sent the fadjar to Openshift, and then he says, oh, well, we have sent everything, the full directory, and we say, hey, there is a Docker file. I know what to do with the Docker file. And it has just executed the Docker file. From, expose, copy, blah, blah, blah. It has also extended it a little bit using labels and environment variable for traceability reason, and done. Then we see this push successful, which is the image is now in the Kubernetes Docker registry. We also have a deployment configuration, which is a default one. We just create one pod. And now everything is fine. So if we go here, we say, OK, take this image and just deploy it once, one pod. So now I'm here. That's my shopping backend. And if I go there, I should have hello. So it's what we expect. And then if I go to shopping, I have nothing because obviously I need to populate the list. So let's try to populate the list. That's my perfect breakfast. A lot of eggs, a little bit of bacon because everything is better with bacon, right? And coffee, a lot. So I have this. This is my list, and now my list is on the cloud. Very well. But if you're using a cloud platform, it's probably for scalability issue, and let's increase the number of pods to 2. So instead to have 1 pod, we have 2 pods now. And now if I go back here, oh, it's working. Perfect. Does that really work? Let's try. Let's go here. Hey, you got an empty list. Oh, you get a full list. Empty list, full list. And here we are facing the first one problem for me, split shopping list issue. Your wife or husband or a friend or roommate has a different view of your shopping list than you. And you are at the grocery store, and when you come back, it doesn't match. So we need to fix that. And obviously what happened here is that both pods are using their internal memory to save the list. And as it's 2 different containers, it's not shared. So we need a shared data repository. Why it's working here and not working with curl? That's the interesting thing. No. I will remove the cache, and you will see it's still, so I'm already removing the cache. It's not the cache. It's a connection affinity. By default, because we're using keep alive inside your HTTP header, we keep the connection, well, the browser keeps the connection open directly to your pod. So there is a connection, TCP connection between my browser and my pod. And we keep it open. So every time you refresh, you are still using the same one. While if I'm using HTTPI or curl, the process stops once it's done that. So the connection is closed. So the next time we run it, it's another connection, and we get the round robin. Anyway, I'm going to use Redis that I have already deployed here to store my shopping list. So I'm not a Redis expert. So if you are a Redis expert, bear in mind that my model of my shopping list in Redis is completely broken. But for this, I will have a Redis client. OK, that's going to be my Redis client. I don't need that anymore. Come on, I'm on the cloud. How do I find my Redis client? Now for this, we are on the cloud, but we're on Kubernetes. And Kubernetes has built-in service discovery. And Vert.x has service discovery too. So we are going to ask Vert.x to create a service discovery. It's going to connect to Kubernetes and report all the services that we have in Kubernetes. And what are those services? They're here. We have the shopping backend, we have the pricer service, we are going to see this one, and we have Redis. Oh, that's a name, that's interesting. I will copy and paste this name. So now I want a Redis data source with the name Redis. That's the name I have in my Docker registry. Obviously, you can also filter services by anything, any metadata. And then it's an asynchronous call. It's a non-blocking call, but it can take time. So I will be called when the service discovery has retrieved a result or not. So I need to check that. If we don't have a service, then the result here, AR, is going to fail, to be a failure, and then we do something like logging the issue in a very meaningful way. Done. We all wrote logs like that. And if we have it, then it's my result, and my Redis is my result. Hey, there is one thing here. This is asynchronous, so it's going to touch the field Redis, but here it's a field. So what about synchronization? Remember, one thread. You don't need synchronization anymore because you cannot have concurrent core. You have only one thread. So this instance is always to be accessed by the same thread. So no concurrent core, no synchronized, no volatile, nothing. Very simple. And then when we have that, let's start the HTTP server. So I need to edit this and to use Redis. So here, oh yeah, I need to do one thing first. Static string key equal show ping. So Redis is a key store, key value data store, and the key is going shopping, and the value is going to be my shopping list. So here, if I do this, I will do hdelete key name. This is also an asynchronous call, but I don't care about the result. I just need to call my get list. Okay, then here it's going to be almost the same. Redis dot h set key name quantity. Our API imposes that it's a string, and again we have a callback here, and I will just call get list. Done. Here it's a bit more tricky. I will do Redis dot h get all. Give me get all. Give me the objects that you have a key. It may be not existing, so if it failed, I will just generate an HTTP 500 HTTP response with that, with the exception like this. And if we have something, then the result is a JSON object. Let's come. So I need to write the response with this now. And I will just do result.encode prettily. And just to illustrate the round robin, I will also add a header xpod using a hack, because in Kubernetes, the hostname environment variable is the pod name. Be careful, this is a hack. Don't use it in production. Or if you do, don't say that I show you this. This is not recorded. Oh, yeah, it is. So now I'm going to redeploy this. Kubernetes is idempotent, so if the object is already existing, it won't do anything. I'm rebuilding my Fedora here, and I'm sending everything to my Openshift. It will say, oh, there is new code here. And it will recreate a new Docker image. Build. You can see it's running already. OK, done. And now is updating. So what we see here is that it's a rolling update. So it's going to start a new one. Then when it's ready, stop one, and so on. The only issue is that we say when it's ready. We're going to come back to that. But now, if I'm going here, so my shopping list is empty, because now I have a data store. But if I put, again, my breakfast inside, oops, Nope. Yeah. Okay. Scripts / populate. Now we are here. Great. So it's there. And if I take this and ask from my terminal, we see Xpod here, which X4 and the way. And if I do it again, I have another one, back to the first one, back to the other one, and so on. So we have the rolling update working now. And both are using the same Redis database. So great. But I said, yeah, there is something here. Is say, when the pod is ready, I'm turning off the first one. I route the request and then turning off the first one. The only issue is that Kubernetes is trying to guess when your application is ready. It doesn't do it right. We have to help it. So to do that, I'm going to my deployment configuration. Here, here we have a warning and health checks. We have two types of health checks. We have readiness and liveness. Readiness is used during the rolling update, and Kubernetes is going to ping my application, and until we get to 200, it will say, you're not ready, you're not ready. Oh, no, you're ready. Liveness is a little bit different. Is if your application crash for any reason, out of memory, disk failure, whatever, it will reboot, it will restart a new pod automatically. Done. We have modified the configuration. As we are modifying the configuration, it's going to run a rolling update because we modified something. So here we have this new color here, which is not ready. So during that time, it's hammering my system until it gets ready. And now it's doing that for the second one. And now we are done. One thing you can look at that is how fast it is to start a Vert.x application, even on the cloud, so which in my case is a VM with a lot of things and so on. So imagine on a truly efficient cloud platform like Google Cloud Platform or Openshift Online, it's even faster. And now we are back on track. But I've done a single microservices, and microservices can be named microservices only if you have more than one. So we need a second one, and the second one is a front end for my shopping backend. And what I'm doing in this one is I'm going to call this pricer service that I found. Where it is? This one. I found this pricer service. I say, yeah, just deploy it. So it's there. That's my pricer service. And for each item I have in my shopping list, I want to call this pricer. Well, if I do that, using callbacks, I'm going to retrieve the shopping list. Okay. And then for each item in my shopping list, I need to call the pricer. But I want to call the pricer concurrently. I don't want to do one by one. I really want to do. So then I will have my, right now, 3 results, and then I need to join them. There's going to be a lot of callbacks. I don't want lots of callbacks. When you start using callbacks, the first thing you will do is to change your indentation settings inside your IDE to 2 space. At least there is no debate about tab versus space. It's going to be 2 space. And if you're really going to this, you are going to use 1 space, but then your code is unreadable and looks like YAML. But, yeah. So, for this, we are going to use Eric's Java 2, which is an implementation of the reactive programming concepts and paradigm for Java. Eric Java 2, as well as Reactor, the pivotal equivalent, both are on the same base, are using reactive streams as basis for their back pressure. So you don't have to care about that. It's done. You just use Flowable and you're done. Back pressure will be done for you. And it's a very good thing because implementing your own publisher is tricky. Anyway, let's try this. I want to do a service discovery. I want to get the pricer service. And I will do the same. But I'm going to use Eric's. I'm going to use HTTP endpoint.eric's get web client, which is a HTTP client for Vert.x. Same thing. I'm going to pass a lambda get name equals pricer service. Again, this name is the name I have here. Here. That's my internal name. This gives me a single. A single is a data stream that can have at most one item. So once the service discovery has completed its call and retrieved the price of service, it will emit this item inside my data stream, and I will get it. Great. Like a feature, right? Same thing. We will see that there is a slight difference between features and single, and it's actually very annoying, well, very confusing when you start. So I will do the same thing for my shopping backend. Shopping backend, okay. And now I have my two services here. Okay, so now I want to have both of them receiving their result. I'm going to use a zip operation that associate data stream, S1, S2, and when both are done, I will have my pricer and my shopping backend, and I'm going to set the shopping backend to S, and the pricer service is to P. Again, I don't care about concurrency here, because with the Vert.x support of Vert.x, everything is going to be called from the same thread. And then I just need this. Return. Again, I say that there is a slightly difference between features and single. And one of them is that if you don't subscribe, nothing is going to be done. So data streams are lazy. I'm pretty sure they are French too. But they're actually not, but I'm sure there is some French idea. If you don't say, oh, actually, I really need the report now, nothing is going to happen. So you really have to say, oh, I'm interested by what you do, and for this you say subscribe. And subscribe is going to materialize all the data streams and execute all the operation. If you don't, nothing happens. And it's very confusing because you start to program, but nothing is done. Okay, so now I have my shopping and pricer, and every time that I'm calling slash, I'm going to call this method, get shopping list. This method is going to call my shopping list service backend, so retrieve the shopping list, and for each item, call the pricer concurrently. So the first thing that needs to be seen here is that I'm going to use a chunk response. HTTP chunk response exists since HTTP 1.1, so it's not related to HTTP 2, it's something that exists, and will let you write your response as soon as you have something to send to the browser. If you get all the results in your, inside your memory and then flush it, your memory is going to be eaten by this. Imagine that you have 10,000 core, then you have 10,000 times this memory. You need to save this memory for the other containers. So what we're doing here is that we just say chunk, and every time I will get an answer from the pricer, I'm going to push that to my browser. So that means that my memory is still perfectly fine. That things that make you container native. And you will see, it's very easy to use. So this is my call to shopping using the web client. I'm receiving a single of JSON object, and the JSON object is my shopping list. So now I'm subscribing, or nothing happened, and now I have my JSON object, but I need to transform this object into a stream. And the interesting thing is that JSON object has been designed to work like that and make, okay, you have a list of entries, let's make it a stream of entries. Like this. Flowable are back pressure support. Observable does not, flowable has. It's kind of confusing about generally use flowable if you think that back pressure is important for you. So now, every time, so I'm going to have my entry here, and I'm going to call my pricer service for each of my entry. So as it's fairly equivalent to this code here, I'm just having a method that does that. Call the pricer for the entry. Okay, and obviously it doesn't compile. Oh yeah, flap map single. Yes. And now, now I need to subscribe again. And we have three possibilities here. The first one is I get my item, my product with my price. And I'm going to write this directly to my HTTP response. response, and product. So what this is doing is just a write using some kind of fake markdown notation. It just write. So instead of doing and, it just write. So we can have an error. That sucks, but it exists. So in that case, I'm just going to fail and generate a 500. Yeah, it makes this pretty. And then, when we have iterated over the whole set of entries, I need to close or to end my HTTP response. So it's going to be server response dot end. I said end and not close because end is flushing it, close is closing it abruptly. So be careful with that. Two methods, but different things. And now I'm done. Normally it should work. So if I deploy this, what's the name? Shopping list backend. And I'm going, instead of redoing the Docker stuff, I'm going to use a Fabricate, a Maven plugin, the Fabricate Maven plugin, Fabric 8. And this is going to do exactly the same thing for free. It's just doing it. So it's going to compute all the configuration, build configuration, deployment configuration. So that's what it's doing right now. The Fabricate Maven plugin knows Vert.x, so it knows exactly how it needs to be configured for that. Then it's going to create the Docker image. That's what it just did here. It's not going to use the Docker file. It's going to use what we call S2I, source to image. Be careful that source doesn't mean source code. It can be binary or source code. Here it's using binary. It takes the source and applies the source to image builder, which is a standard way defined by your ops team to run your Java or whatever application. So your ops team has done that, and if you remember before, my build file was very, very simple, and it was 8 something like that. If 8 steps. If I look here and look at my log, it's 24 layers. Yeah, because ops are verbose. They like adding stuff like, oh, we need a monitoring agent, we need logs, we need a lot of things, we need to customize the JVM and stuff like that. And one thing, and Nicola is here, so Nicola is maintaining this. Can you finally remove this checking Spring Boot archive? Is this not Spring Boot? This is Vert.x. So please remove this trace. Thank you. Please all vote for the GitHub issue, so you will have to do it. So now we have my shopping list service here. It's exposed under this route here. And here it is. So what we see here is that it retrieves the shopping list, and for each entry, it's called the pricer. And that's a response from the pricer. It's calling them concurrently. So let's see this. Remember, I've used a pricer service, and this pricer service can be slow. Oh, toggle. In slow mode, it takes 3 seconds to answer. So if we would have called for each entry sequentially, we would call the first one, wait for 3 seconds, call the second one, wait for 3 seconds, call the third one, wait for 3 seconds. Here, we are going to wait once because we actually emit all the requests at the same time. All will be timed out by 3 seconds and, well, block for 3 seconds and get back. So instead of waiting 9 seconds, we are just waiting 3. I think it's 5 seconds and not 3, so just replace. But we don't want this because this is slow. Even if it's just 5 seconds, it's still too slow. So we need to protect our call with something. And this something is called a circuit breaker. So I'm going to create a circuit breaker. Vert.x comes with its own circuit breaker, this one. You can use these tricks. You can use whatever circuit breaker you found, but circuit breaker is Vert.x respects this one thread IDE. It's very responsive, and it has been made to be used in a single threaded environment, which gives you a lot of optimization. It is. So I've just created a circuit breaker. This circuit breaker, so what it is, it's monitoring a call between my shopping list backend and shopping list and shopping backend. And every time that there is a failure, it will increase the counter. And once this counter reach a threshold, here 3, it's going to stop calling the service and call a fallback. But anyway, we are going to call back to call this fallback every time we have a failure. If the call doesn't answer in 1 second, it's considered as a failure. And when we stop calling the service, periodically we will try to see if the service is back. This is this 5-second timeout here. And so we go in a third state, and in third state we let the next invocation go to the shopping backend to check whether or not it's back on track. So once I have my circuit breaker, I need to protect the call, so change here. So here I'm going to use a circuit rx execute command with fallback. I have my entry, my future here. Shopping that retrieve pricer, entry, and future. So this future object, which is not a single, it's only a future, will let me report whether or not the call was a failure. And if it was a failure, an error, I'm going to write some default value. And we are done. I've used a circuit breaker. Oh, why it's not compiling? You need a JSON object? Okay, sorry. I forgot a couple of keystrokes. Yeah, and I need to return that. Done. Oh yeah, and now you don't need JSON object. Great. No, you do. Ah, interesting. Interesting. If I would, it says that it's not required, but if I don't, it doesn't compile. Yeah. Okay. Great. So now let's deploy this again. So now what's going on with this circuit breaker? It's going to call my process service, detect that it's not working because it's too slow. So calling it second times, calling it third times, then go to this, what we call open state, and stop calling the service. So it will immediately call the fallback. After 5 seconds, it will let the next call go to the shopping backend to check whether or not the shopping backend is back on track. And if it's back on track, say, okay, we are going to call it again. And if it's not back on track, then go back to this open state and not call it. And after another 5 seconds, it will retry. So circuit breaker is actually very important in microservices because it supports respect. When you have a service that is flaky, start to be tired, start to be old, under update, or something like that, not in good shape, it's useless to continue hammering it because you make things worse. Keep it some hair, well, give it some hair so it can recover. And once he has recovered, start kicking it again. So circuit breaker is very important for that. And because he has this auto recovery loop, it's very simple to use and very reliable. So we're still in slow mode. So if I call that, we wait 1 second and then we say, oh, this is not normal. So I'm calling my fallback, and my fallback is a tribute to JavaScript, is not a number. So, and again, and now, it's fast. And after 5 seconds, it will let one call here go and to check if it's back on track or not. So let's go back on track and toggle the process service in normal mode again. So he has let one call pass, and now in the next call, everything should be fine. And yes, and now we're doing the service again. Yes. Sorry? Inbound. Well, that's all I have. Oops. Thanks. Yeah. No. Thanks. Is that there? Yeah! I found my URL. No. It doesn't work. Yeah, does it? No. It's resolving host. That doesn't sound good. Resolving host? That's weird. Let me check the URL again. That's in the pricer. Yeah. Come on. Ah. Okay. Distributed systems are hard. See. I should have used the circuit breaker, by the way. So that's what I have. In this 45, 50 minutes, we have developed a couple of microservices. We have seen why it's important to use the right runtime or toolkit if you want to embed them inside containers, because containers is about sharing. It's not only about isolating your process. You are sharing the same infrastructure. Vert.x has been made with this reactive ID in mind since the first line of code 5 years ago. It's not something we have added as an afterthought. It's something we designed initially with this ID. So yes, during these last 4 to 5 years, we had success and failures, because obviously reactive requires a mind shift. It's hard. If you are used to synchronize blocking code and you want to switch to non-blocking asynchronous code, it's not something you will do in a daytime. It's something that takes a couple of weeks, but once you use it, it's great. We have used callbacks. We have used Eric Java 2. That's just the beginning. Do we have Kotlin user here? Kotlin. Oh, you don't like Kotlin? Kotlin is great. You should look at Kotlin. Kotlin has a great idea, coroutine. Well, great idea. It's something that comes from the 60s. So I like coroutine. The idea behind coroutine is that you write your code as you will do today, except that you have 2 new keywords, await result and suspend, and actually it's going to do the asynchronous for you. So your code looks like the flow you are writing right now, but because we have these 2 keywords, it makes things much simpler for the migration if you are used to this type of code. Depending on the language you use, we provide different constructs. Like if you are using Scala, use features, because the features in Scala are great. They're really built in the language in a nice way, and all their API is based on that, so it's very cool. If you are using, I think that's, yeah, Groovy or Ruby, we also have construct for this. If you're interested by Vert.x, you have the URL here. Here you have a free mini book. It's 70 pages about almost what I just said, how to write reactive microservices and why it's important to write microservices a reactive way in a container native fashion today. If you're interested by Openshift or Kubernetes, check this URLs here. And if you will say, okay, well, you explain why I should not use traditional way inside the containers, because obviously threads are bad for my containers. But there is one other thing about Vert.x. Vert.x is about freedom. It will let you shape your system as you want, not as the framework is telling you to do it. You are completely free to do whatever you want. So yes, the first time you say, but how I will do that? So you have to become creative again and stop thinking that everything said by the framework has a great ideas. Thank you. Yeah, we have a question over there. Front-end question. Wow, did you have seen my front-end skills? They are inexistent, so. Yep. The circuit breaker, yes? Timeout doesn't block the thread. Timeout tells you when the timeout is done, but doesn't block the thread. So the thread can handle the other request while the first request is waiting for the timeout. Yep. If you have lots of requests, because we are all non-blocking, even a timeout is non-blocking. Timeout doesn't mean that I block the thread. The thread is never blocked. A timeout is just something say, oh, give me a call once the timeout is done. But I'm not blocking. I can handle the other requests during that time. And once the timeout is reached, then I get a notification to say, The timeout is reached. Did we add an answer or not in the meantime? But the timeout doesn't block the thread. It's the thing here. A timeout it's just like a reminder inside your phone or whatever. When you say, okay, tell me in 5 minutes. Are you waiting with your phone like that for 5 minutes, or can you do things for 5 minutes? You can do things for 5 minutes, right? Same thing here. It will just snooze after 5 minutes and tell you, oh, another 5 minutes are done. What do you want to do? Another question? Are you all hungry? Thank you very much.